Yes. Last time I told you about nature of radiation. I told you various terms which are used as far as radiation is concerned: speed of light, wavelength, frequency, amplitude, and wave number. Now, if we arrange all different wavelengths, all different types of radiation in a particular order, all, then the entire range which is obtained, that is called electromagnetic spectrum. So write down, next topic is, heading is electromagnetic spectrum. Electromagnetic spectrum. And it is the arrangement of all electromagnetic radiations, all electromagnetic radiation in their increasing wavelength or decreasing frequency. Because wavelength and frequency, they are inversely proportional to each other. Remember, last time I told you C is equal to nu lambda. It means frequency and wavelength, they are inversely proportional to each other. So we can say either arrange in the increasing wavelength, or we can say in the decreasing order of their frequency. Continue. It's different regions. It means different regions of electromagnetic spectrum. Its different regions have different names and different uses. Different names and different uses. I'm giving 4 to 5 different regions, their names, their frequencies, and what they are used for. That I'll tell you. You please write that in the table form. Region. Name of the region, right? Frequency. Units of frequency will be hertz. I told you units of frequency last time. Uses. Now write down. First region, microwave region. First region, microwave region. Frequency is of the order of 10 hertz. And it is used in radars. Radar means to locate the position of aircrafts. Now, subsequent, I'm dictating, I'm not writing on the board. Right, next, write on number 2. Radio frequency. Radio frequency. 10⁶ hertz. Uses broadcasting. Broadcasting means on radio you listen to various programs, FM channel and others. That is radio frequency region. Next, infrared. Infrared. Frequency 10⁻13. Uses heating. It's used for heating purpose. Next, visible light. Number 4, visible light. This is that range in which we can see, right? Frequency 10⁻15. 10⁻15. Uses light visible to our eyes. Light visible to our eyes. Last, UV, ultraviolet region. Frequency 10⁻16. Uses component of sun's radiation. Radiation which comes from sun, its component is UV radiation. Next topic. All these small topics will be used in subsequent topics which will be starting today. Next topic, dual nature of dual nature of electromagnetic radiation. Electromagnetic radiation. See, look here. Let us say I'm holding this torch. Light comes out from this front portion of the torch. When light comes out, it does not go in this narrow path only. It spreads in various directions. This spreading, this scattering of light is called diffraction, right? This is called diffraction. Second term which we'll be using, that is called interference. Let us say there is stagnant water. We throw a pebble, we throw a stone in it, then ripples will be formed, waves, ripples will be formed, right? And they become wider and wider circles. Let us say we throw two stones at a time, ripples of both waves will come closer and closer and ultimately merge into each other. This merging of waves is called interference. So, two important terms regarding waves. One is diffraction and the other is interference. And these are two characteristic properties of waves. If you remember, last time I told you that any radiation is transmission of energy in the form of waves. So, radiation is nothing but waves. And waves have two characteristics, which I told you just now, diffraction and interference. Or I can say anything which exhibits these two phenomena, diffraction and interference, confirms wave nature of that particular object. Right? Now, start writing. This is something which we'll be using today itself. Heading, dual nature of electromagnetic radiation. Yes, spreading of waves when when they pass through an obstacle or narrow aperture like torch is called diffraction. Is called diffraction. Full stop. Merging of waves is called interference. Interference. Diffraction and interference are typical properties of waves. Radiation from any source exhibit both these properties, which confirm wave nature of radiation. However, following observations cannot be explained. Following observations cannot be explained on the basis of wave nature of radiation. Cannot be explained on the basis of wave nature of radiation. See, there are 3 points, 3 phenomena which cannot be explained on the basis of wave nature of radiation, which I told you just now. It means apart from wave nature, any radiation is associated with some other type of nature also, and that is called particle nature of radiation. So particle nature plus wave nature of radiation will be called dual nature of radiation. That's what is the topic. So what are these three phenomena which cannot be explained on the basis of wave nature? Write down. Number one, black body radiation. Black body radiation. Number two, photoelectric effect. Photoelectric effect. Number three, line spectrum. Line spectrum of hydrogen. Line spectrum of hydrogen. And these three phenomena, they become our next three topics. So we take up first topic, write the heading, black body radiation. Black body radiation and Planck's, Planck, Planck's quantum theory. Planck's quantum theory. Now, chapter will become gradually difficult, right? Easy part is over. Chapter will become gradually difficult, and subsequent chapters will be based on what we study towards the end of this chapter. First of all, what is a black body? Black body is not that body which is black to look at, which is black in color. No. In fact, black body is any such body which can absorb and which can emit radiation of any wavelength, any frequency. Right on. That body which absorbs and emits radiation of all wavelengths is called a black body. Is called a black body. Radiation emitted oblique absorbed by a black body is called black body radiation. Is called black body radiation. I'll explain in parts and dictate in parts. See, you might have seen on some YouTube, or might have experienced, if we have an iron rod, let us say we take a nail and we heat it on a flame, gas stove. As temperature increases, first it becomes dull red, it starts glowing. We increase the temperature, it becomes bright red. And if we increase the temperature to a very high level, it will become orange. It means as the temperature increases, the glow which it produces, that color of that glow will keep on changing. See, when we increase temperature, color of glow changes because more the energy we supply, more is the energy which it will emit. So glow is due to the energy which it is emitting in the form of radiation. It means higher is the energy supplied, higher will be the energy which it will emit, and higher is the energy emitted means higher will be the frequency of radiation emitted. Why did I say that? See, I told you this relation last time. No, not this one. This, of course, this will be coming. We'll study this relation today. So when we supply more and more energy, it will emit out more and more energy. Color changes means with increase in energy of radiation emitted, frequency of the radiation will also increase because E is equal to h nu. H is a constant that I'll tell you in this very topic. Now, why is there absorption of energy? Why is there emission of energy? And how it is related to frequency of the radiation? All that we'll be studying in this particular topic. As I said, I'll dictate you in parts. Right on next paragraph. When a solid body, when a solid body is strongly heated, it starts glowing. It starts glowing. That is, emits energy in the form of radiation. For example, so it's very simple. If you heat that nail or rod of iron and immediately take it to a dark room, you'll find as if there is glow in that dark room. It means energy is being emitted in the form of radiation. Although we supplied energy in the form of heat, but it is emitting energy in the form of radiation. Continue. For example, when an iron rod is heated, color of radiation emitted gradually changes from dull red to bright red to orange with increase in temperature. With increase in temperature. For temperature, please write on T. This is due to increase in frequency of radiation emitted with increase in temperature. Next paragraph. Now the question is, when we increase temperature, correct, more energy has been supplied, more energy is being emitted, and if more energy is being emitted, why is the color of radiation changing? This cannot be explained on the basis of wave nature of radiation. This can only be explained on the basis of a theory which was given by Planck, that is called Planck's quantum theory. And this theory was later modified by Einstein. And overall, in this theory, we talk about particle nature of radiation, right? So we gradually come to particle nature of radiation. So anyways, right in the next paragraph, this observation cannot be explained on the basis of wave nature of radiation, but can be explained on the basis of Planck's quantum theory. Planck's quantum theory. Now we have come across a new term, quantum. What is a quantum? See, quantum is the smallest packet of anything. Smallest packet of anything is called quantum. Charge on an electron is the minimum charge on a particle. So I can say charge on one electron is one quantum of negative charge. Similarly, charge on one proton is the smallest positive charge on a particle. So charge on a proton can be called one quantum of positive charge. See, if you buy a packet of milk, if you go to Mother Dairy or you go to a shop and buy a packet of milk, the smallest packet of milk you'll get is half liter. If you want 750 milliliters of milk, you will either have to buy half liter or you'll have to buy 1 liter of milk. That is 2 packets of half liter each, or you can buy one packet of 1 liter. But you cannot buy 750 milliliters of milk. It means the quantum, the smallest packet of selling milk is half liter. So half liter is the quantum of selling milk by various like Mother Dairy and other outlets, right? Similarly, the smallest packet of energy, it may be in any form, smallest packet of energy is called quantum. And the quantum of visible light is called a photon, right? So photon is nothing but quantum, but photon is a quantum of smallest packet of visible light. Now start writing in the next paragraph. uh, smallest packet of anything is called a quantum. For example, an electron carries minimum amount of negative charge, while a proton carries minimum quantity of positive charge, due to which charge of electron and proton is called one unit of, is called one quantum of negative and positive charge respectively. Smallest packet of energy absorbed or emitted by a particle is called a quantum of energy. Quantum of visible light is called a photon, 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 or particle of visible light, Next paragraph. For this, again, I'll have to explain something. Today, you know that the structure of atom, according to structure of atom, there's nucleus at the center, and this nucleus is surrounded by orbits. Electrons are moving in these orbits. And as we move away from nucleus, as we go to higher and higher orbits, energy of orbit, or we can say energy of electron present in the orbit, will keep on increasing. Let us say energy of this orbit is 10 joules. This is 20 joules. This is, let us say, 28 joules, and so on. If electron is present in shell number 1 and we supply energy in the form of heat or light, means we are supplying packets of energy. For electron to jump from shell number 1 to shell number 2, it has to absorb 10 units of energy. Now, important thing is coming. So for electron to shift from shell number 1 to shell number 2, it has to absorb 10 units of energy. Remember, electron will either absorb 10 units of energy or it will not absorb at all, because it will absorb energy in the form of packet only. It's not that electron absorbs 1 unit plus 1 unit plus 1 unit. It will not absorb energy in parts. It will absorb energy in the packet of 10 units only. And this packet of energy is nothing but quantum of energy. If the electron goes directly from first to the third shell, it has to absorb 18 units of energy. It means it will either absorb 18 or it will not absorb at all. But at the same time, let us say we supply an energy of 15 units. Out of 15 units, it will absorb 10 units of energy and will shift from shell number 1 to shell number 2. Remaining 5 units of energy will be wasted. It will not absorb, because the quantum for shifting of electron from shell number 1 to shell number 2 is 10 units. Similarly, if I supply 30 units of energy, electron will absorb 18 units of energy and jump from shell number 1 to shell number 3. Remaining 12 units of energy will not be absorbed. This is the meaning of quantum, and we call it quantization of energy. Now, once the electron has absorbed energy, it has gone to a higher shell, it will become unstable. Remember one simple sentence: more the energy, lesser the stability. If energy is high, stability will be less. And every substance has the tendency that its stability should be maximum. And for maximum stability, its energy should be minimum. So when we supply energy in the form of radiation or heat, electron absorbs energy, goes to a higher shell. Depending on how much energy it has absorbed, it will go to some higher shell. In the higher shell, its energy is high. That is, stability is less. Now, to stabilize itself, it will lose its extra energy which it has absorbed. And when it loses energy, extra energy which it has absorbed, it will come back to its original shell. And this loss of energy will always be in the form of radiation. Now recall, I told you about iron rod being heated. When we supply less amount of heat, color of that rod becomes dull red, because electrons might have gone from one shell to some next shell. If we increase the temperature further, electrons might have gone to a much higher shell. If we further heat, electron might have gone farther away from the nucleus. Means energy keeps on increasing as we increase the temperature. In higher shell, it has become unstable. To stabilize, it will lose energy and it will come back to its original energy level. So more the energy supplied, more the energy it will lose. More the loss of energy, or lesser the loss of energy, that will be reflected in the color of radiation emitted. I told you, color of this rod becomes dull red to bright red to orange with the increase in temperature, right? This is the main purpose. This is the main idea of absorption of energy and emission of energy in the form of packets of energy, that is quantas of energy. Now write down. Next paragraph. I told you about photon. Next paragraph. According to Planck's theory, a particle, that is electron, present in an atom or molecule or ion, can absorb or emit energy only in the form of fixed packets of energy, that is quantas. So this absorption or emission of energy does not take place in a continuous manner. Now, what is the meaning of continuous manner? Although I told you, continuous means if electron wants to go from shell number 1 to shell number 2, it will not absorb one unit of energy. It will not absorb energy in a continuous manner, small energy. No, it will absorb energy in the form of packet of 10 units only. So that is absorption in the form of quantum, not in a continuous manner. Next paragraph. On heating, electrons present in the valence shell of atoms absorb fixed quanta of energy, and they are promoted to higher shells where they become unstable. To stabilize themselves, they lose energy in the form of radiation of quantas, that is particles. Next paragraph. Now we are coming to the mathematical part. Energy of quantum oblique photon, is directly proportional to the frequency, and inversely proportional to wavelength of radiation. Write down the equation. E energy directly proportional to frequency. So if we supply energy in the form of radiation, energy supplied will be directly proportional to frequency of radiation. But we can supply energy in the form of heat, light, electricity, in any form, right? Emission of energy will be in the form of radiation, right? or I can say E is equal to a constant. This constant is H, called Planck's constant, that I'll tell you later. Or I can say E is equal to hc by lambda, because c is equal to nu lambda. Last time I told you velocity of light is equal to frequency into wavelength. In place of frequency, I've used c by lambda. So these are two relations which we'll be using. Label H. This is called Planck's constant. Planck's constant. Note down its value. It is 6.625 into 10 to the power minus 34. 6.625 into 10 to the power minus 34 kilogram meter square per second. 6.625 into 10 to the power minus 34 kilogram meter square per second. With the same value, it has another unit also, or I can say 6.625 into 10 to the power minus 34 joule second. In place of kilogram meter square per second, you can use joule second. Now continue. Let us say we have a piece of, again, say iron. It has many atoms. One electron at a time will absorb one photon, one quantum of energy. If there are, say, 1 million atoms, then one electron of each atom, it means 1 million electrons of 1 million atoms, will absorb 1 million photons. It means total energy absorbed by that piece of metal will be number of photons which it absorbs or which it emits multiplied by the energy of one photon. See, look here, energy of one photon is h nu or hc by lambda. In case it absorbs x number of photons, in case it releases x number of photons, then the total energy absorbed or total energy released will be x times this value. Write down. Next paragraph. according to Planck, a body can emit or absorb whole number quanta, fraction nahi, not fraction, whole number quanta, so that the total energy emitted or absorbed by a body is a whole number multiple of h nu and hc by lambda. Copy from the board. That is, E is equal to n into h nu, or I can say n into hc by lambda. If one photon is absorbed or emitted, value of n is 1. If 10 photons are emitted or absorbed, total energy absorbed or emitted will be 10 times h nu or 10 times hc by lambda, right? So n will always be a whole number. So based on this, we'll solve one numerical. I'm sharing this numerical on your WhatsApp. Yes. In the video, you'll find this as in text numerical 3 in the description box. Yes, numerical is calculate energy, frequency, and wave number of photon of wavelength 200 picometers. So there are three parts of the numerical. First, we'll calculate energy. E is equal to hc by lambda. H is constant, c, that is velocity of light, is constant, and lambda is given. H is 6.625 into 10 to the power minus 34. Think of its units. Units are joules second multiplied by velocity of light 3 into 10 to the power 8 meter per second divided by lambda. We are given lambda in picometers. Since we are using meters per second, we'll have to convert lambda into meters. This is 200 picometers. It will be 200 into 10 to the power minus 12 meter. So when we solve, this will give you one first answer, that is 9.9375 into 10 to the power minus 16 joules. This will be first answer. Second, we have to calculate frequency of the radiation. Now, for frequency, use the relation C is equal to nu lambda. So frequency will be value of C 3 into 10 to the power 8 meters per second, lambda 200 picometers. Automatically units will also come. This will give you second answer. This is 1.5 into 10 to the power 15 second inverse. This is second answer. Third part of the numerical is we have to calculate wave number. Last time we told you wave number is equal to 1 by lambda. Lambda is 200 picometers. This will be the third answer. That is 5 into 10 to the power 9 meter inverse. Meter inverse will be the unit. 5 into 10 to the power 9 meter inverse. So with that, we finish what you call black body radiation. Wait a minute.